Okay, welcome back. We start off today with Volodymyr Nekrashevych from Texas A&M, and he's going to talk about topological and conformal dimensions of self-similar groups.
Yes, thank you very much. Thank you very much for inviting me here. So I'll talk about self-similar groups and their limit spaces. And I just realized yesterday that that I gave probably the first talk about limit spaces for similar groups in this room in 2001. And also during that conference, in a discussion with Laurent Bartholdi, we realized that there must be a connection of this topic with holomorphic dynamics the first time. And then later we really proved that limit space is Julia set over rational functions. So similar groups are algebraic object describing some dynamical systems. In larger generality, one has to talk about not topological spaces, but Orbi spaces, but that's a technical notion, so I'll kind of swipe it under the rug and talk only about topological spaces, reminding sometimes when Orbi spaces are needed. So essentially, it's self-similar contracting groups. They describe, in a unique way, actually, locally expanding coverings. So if you have X as a matrix, compact matrix space, a metrizable space, and this is a covering map, and we require it to be locally expanding, so there exists epsilon and L greater than 1, such that distance from f of x to f of y is greater than L distance of x from x to y for all xy, such that the distance is at most epsilon. And there is a bijection between topological conjugacy classes of such maps and the algebraic objects, which I will describe. And today I want to talk how properties of this space X, like topological dimension, are reflected in the algebraic structure of the corresponding object. Also, such maps, such spaces have kind of canonical quasi-symmetric class of metrics, and we'll talk about conformal dimension. So in order to introduce the groups, and for other reasons, I will actually relax this definition, make it more general, and we'll talk about virtual endomorphisms of spaces, virtual endomorphism of topological space. It consists of two maps. One map between two spaces. One map is a covering. Yes, topological sense. Yeah. Well, locally, the local homomorphism is a little slightly more general than covering. Yeah. So a covering map, and then another map. Let's call it phi. Also in the same direction, just continuous. So ideally, I'm thinking still about this case, and in this case, phi is identity map, but I want some freedom, so phi is my pretend identity map. But so finite degree covering. So virtual endomorphism, it's virtual because you are going to a covering, and then you use a map. So that's where virtual appears. So assuming that x0 is connected, path connected, then an actual algebraic object associated to this is the virtual endomorphism of the fundamental group. Namely, you identify fundamental group of x1 by the covering map with a subgroup of finite index in the fundamental group of x0. So that's isomorphism. So basically, you take the inverse of it. That will be mapped from pi1 of x0 and then compose it with phi, you get again a map. Okay, so this is it's not a map, it's a virtual endomorphism in the sense that domain is a subgroup of finite index. Maybe I should write it that way. So you have H, and this is a subgroup of finite index in phi1 of X. So this is the fundamental group of X1, but we identify it with subgroup of finite index of X0. So we get a virtual endomorphism or a homomorphism from a subgroup of finite index into the group of the fundamental group. In principle, that's the algebraic object that I'm interested in. And by the way, this is defined only up to inner automorphisms of the fundamental group. But I want to describe a little bit this in more detail and describe an equivalent object, which actually will be what I will call the self-similar group. So let's go back to the case of virtual endomorphism. So we have a covering map, and then the other map. So let's now be careful. Let's choose a base point for the fundamental group. Then this is a finite degree covering map. So we have the set of preimages F inverse of T. That's a finite set because I assume that covering is finite degree. And let's identify it bijectively with some finite set, with some alphabet, call it straight X. And then for every, okay, never mind. Let's say that this is T1, T2, and so on, TD. And this way I'll identify it with indices from 1 to D bijectively. And then let's choose connecting paths from the base point to the image of each of these TIs and call this connecting path Li. So we have fiber of the covering map. It's a set of points of X1. We map them to X0, back to X0, and then connect the base point to them. Now, suppose you have an element of the fundamental group, gamma, a loop. Then we'll lift it by the covering. We'll get some paths starting and ending in the points of the covering, on the points of the fiber. So we get a permutation of the fiber. And if you identify these fiber with indices from 1 to D, we get an element of, let's call it sigma, an element of SD, the permutation, the monodromy permutation that you get. Now let's map these curves back to X1 by phi. So we'll get this similar picture here. And let's connect the base point by the chosen paths to these. And then we'll get loops. For every point Ti, we get the lift and these two connecting paths. Together we get a loop. So for each I, we get a loop. And therefore we get some collection of loops, gamma 1, gamma 2, gamma D. Where gamma I is the loop, is this triangle. We have Li, then the corresponding lift, image of the corresponding lift, and then the corresponding L sigma Y. So we get a permutation and we get a D-tuple, so an element of the fundamental group raised to power D. So we get an element of the symmetric group and an element of the direct power of the fundamental group. We can put them together. So we get this and treat it as an element of the semi-direct product of SD and fundamental group raised to power D. So the Riesz product. So every loop defines an element of this Riesz product. And it's easy to see, just drawing the picture, that this is a homomorphism. So we get a homomorphism from the fundamental group to the Riesz product. So that's, you can reconstruct this Riesz product just from that virtual endomorphism. So I haven't introduced any new algebraic structure here, but it will be more convenient to work with this object than with the virtual endomorphism. So this is what we call self-similar group. A self-similar group is a group T together with a homomorphism from G to a metric group to the Riesz product with a symmetric group, and up to inner automorphism of the Riesz product. So we are allowed to compose, because here we have made some choices. We can choose different base points, we can choose different connecting paths, we can choose different identification of the fiber with indices. All these choices amount just to composing this map with an inner automorphism of the symmetric group. So we are always allowed to change, to apply, to post-compose this with an element of the, with conjugation. Okay, now, traditionally, these homomorphisms, yeah. No, absolutely no. It's almost never on to. In interesting cases, and okay, I guess I need examples to show you examples. As an example, we can take the covering F of the circle onto itself. In this case, phi will be the identity map, and the map F is double covering. It's you angle doubling map. And then you can take the base point 0, and the fundamental group is cyclic, generated by the loop. So let's A be the generator. So the loop. Okay, I'll draw this circle as the unit circle on the complex plane using the exponential map. So this is our A. So the lift of this, the lifts will be two semicircles. So if you take square root in complex plane, you get this. And then if you take this as a base point, its preimages are these 2 points. And we take the trivial path as one connecting path, and this path as the other connecting path. Then we see that this element, it permutes the fiber. So the element of the symmetric group is the transposition. Let's use 0 and 1 as indices. So transposition 0, 1. If you start here and lift, you get this path. If you complete it by the connecting paths, you see that you get trivial element of the fundamental group. But if you take this preimage and complete it to a loop using connecting paths, you get this loop, you get A. So A is mapped to transposition and then 1, A as the element of the Riesz product. So traditionally, we look at these Riesz, we call this Riesz recursion. Riesz recursions are as a recursive definition of action of the group on a tree. So if so we have our alphabet is 1, 2, up to D, these indices, and then we have a tree of words, finite words, the free monoid generated by this, where word V is connected to word Vx. And then this permutation, this element of the Riesz product, so the statement that gamma is mapped to this element of the Riesz product, it's a recursive definition saying that if gamma acts on this tree, sigma is how it describes how it permutes on the first, how it acts on the first level. Sigma is the action on the first level. And then gamma 1, gamma 2 through gamma D tells you how you act on these subtrees. Or in other words, it says you that gamma applied to words starting with I is equal to sigma of I, and then gamma I applied to W. So this way, we can continue. We can apply the Ritz recursion to gamma I and know how it acts on the remainder of the word. And this can be interpreted as iteration of this map. So you can iterate this map. You have this Ritz recursion, then you apply Ritz recursion to each coordinate. You get an element of Ritz product, well, SD, Ritz G. Then again, you apply it. So we can iterate it. And this iteration is exactly the description of the action on this rooted tree. Now, there was a question what we assume about these homomorphisms. We don't assume anything. So it may happen that many elements of the group act trivially on this tree. So the action of some elements may be identical. So it's natural to take the quotient by the kernel of the action. So the quotient of G by the kernel of the action on X star is called the faithful quotient of G, and it is also a self-similar group, basically with the same Ritz recursion. Just you apply the epimorphism to everything. That will be well-defined Ritz recursion on the faithful quotient. Conversely, I will need the opposite direction. So the original group, self-similar group G will be called a cover, will be called an overgroup of the faithful quotient. So sometimes I will be interested in the opposite direction. And by the way, this iteration of the Ritz recursion, it corresponds precisely to iteration of the virtual endomorphism, of the topological virtual endomorphism. What does that, how do you iterate? Of course, if in this case, when phi is identity, iteration is literally this, the usual iteration that you iterate the map. But in the general case, when there's the other map phi, iteration means fiber product. So if you take a virtual endomorphism, then its nth iteration, Fn, the domain changes, becomes a different space, where Xn is defined as the space of all sequences x1, x2, xn of x1 to the power n, such that so they are like forward orbits. So f of xi, I want to write is equal to xi plus 1, but that's impossible. They're in different spaces. And remember that phi is pretend identity map. To say that this is phi of I xi plus 1. So it's exactly pull back if you can, it's fiber product. And then phi n of x1, x2, xn is by definition f of xn, and phi n of x1, x2, xn is phi of x1. So again, if phi is the identity map, that's just the usual iteration. If phi is something else, that's a little bit different. Okay, so one class of, yes, and I forgot the main thing, this so similar group, rather its faithful quotient, associated with the virtual endomorphism is called the iterated monodromy group of this virtual endomorphism. So a classical, an important class of examples comes from holomorphic dynamics. If you have f of x, f is a rational function seen as a map on the Riemann sphere. And suppose that it is, suppose that orbit of every critical point, forward orbit of every critical point is finite. So such maps are called postcritically finite. Then we get a nice virtual endomorphism, namely let P be the union of these orbits. So you take all critical points, actually don't need critical points, critical values, so values at critical points, and their forward orbits. Take all of them together. Because it's forward invariant, F inverse P contains P. And so we can take x0 to be the sphere without these points, x1 to be the sphere without their preimages, and then F will be, because we removed critical values, this is an honest covering map. And because of this inclusion, the identity inclusion will be a continuous map from x1 to x0. So this way we get a virtual endomorphism, and the iterated monodromy group of this virtual endomorphism is called the iterated monodromy group of the rational function. So for example, this example is for z square minus, for z square is exactly the iterated monodromy group of z square. Those critical points are 0 at infinity, they are fixed. If we remove them, homotopically it's the same as circle. Another example is z square minus 1. That's exactly the group we discussed with Laurent 22 years ago here. Okay, so now I mentioned that this algebraic object, the iterated monodromy group, is a complete invariant. Of course, not in general, but in for special class of dynamical systems, namely for hyperbolic ones. What is a hyperbolic? Well, namely for these. So this is expanding case. In the expanding case, the iterated monodromy group is a complete invariant. But again, I prefer to talk about virtual endomorphism. What does expanding correspond to in the sense of virtual endomorphism? Here we have to go kind of other way around because it's easy to lift metrics by the covering. So we will assume that the covering is local isometry, and therefore expanding means actually contracting for the other map. So let me give the definition and formulate the first theorem. And then I will be ready to talk about dimension. So we say that virtual endomorphism from x1 to x0, from x1 to x0 is, let's say, contracting, but by contracting, I mean essentially the same as expanding. So we say we assume that x0 is compact metric space. F is a local isometry, and phi is contracting, strictly contracting, or locally contracting, doesn't matter. So under these, if these conditions are satisfied, we say that virtual endomorphism is contracting. Now, theorems is that let f phi from x1 to x0 be a contracting virtual endomorphism then the limit So if you take x0, x1, x2, and so on, remember these spaces, and with respect to map that maps x1, x2, xn to the phi image essentially. So phi goes to x1, x2, xn minus 1. So the inverse limit with respect to these maps will denote it x infinity, and the induced map. So this inverse limit x infinity, just by the way is defined, it is the same as the space of all infinite sequences satisfying the same condition, that f of xi is phi of xi plus 1. So essentially forward orbits of f. If you think that phi is identity, this is a infinite forward orbit of f, and we take the space of all infinite finite orbits as a topological space, and the map x1, x2, xn, and so on, map to x2, x3, and so on. So the shift depend only on the iterated monodromy group. Up to topological conjugacy. So you take this algebraic object, an abstract group with a homomorphism into Reith product, and this algebraic object uniquely determines this dynamical system. It doesn't matter what was the original virtual endomorphism. As soon as if you take two such virtual endomorphisms, as soon as they are the same on the level of pi 1, the limits are the same. So as an example, let's consider the case of rational functions. Say, or to be more concrete, let's take the z squared minus 1. So if you have a rational function, critically finite rational function, and take that virtual endomorphism that I defined, like sphere with punctured, so punctured sphere, we remove the postcritical set, as we did it here. What we could do, we could take the Poincare metric, assuming that there are more than 2 points. That punctured sphere is a hyperbolic surface, so we can take the Poincare metric on it, and also we can take the Poincare metric on the other punctured sphere. We take Poincare metrics on these punctured spheres. F will be local isometry, and then phi will be contracting by what is it? Essentially by Schwarz lemma, but it's not uniformly contracting, and the space is not compact. But you can remove, instead of points, you can remove some open disks, and then restrict that Poincare metric from punctured sphere onto this compact set, and you will get a uniformly contracting map phi. So you will get this virtual endomorphism will be contracting. And then the limit space, this limit space will be the space of forward orbits. And if you are in this compact case, these forward orbits, it's easy to check if you know something about holomorphic dynamics, that this space of forward orbits is exactly the Julia set of the rational function. So this space that depends only on the iterated monodromy group is the Julia set of the rational function, and the shift map is the action of the rational function. So for example, if you take z squared minus 1, so one way of doing it is, so the postcritical set is 0, -1, and infinity. You can remove infinity, so you'll get a disk. You remove something around -1 and around 0 to get this topological space. That's x0. It will be covered by something like this. So preimages of these are 0, 1, minus 1, infinity. They will get 3 holes. So that will be isometry, and phi will embed this, well, like this. So that will be a model, and by this theorem, it will converge to some space. And if phi is an embedding, then this is exactly the intersection of domains. If phi is identity, identical embeddings, then this X infinity is intersection of domains of the coverings, of the partial coverings. So that's one way of seeing that it is the Julia set. But here, as I said, if you have the same thing on the level of pi1, you will have the same limit. So instead of doing it on a Riemann surface, we could imitate it by some other space. For example, we can replace this picture by any homotopy equivalent picture. So here we have a disk with 2 holes, so it's homotopically equivalent to 2 loops. Picture here is homotopically equivalent to this. And the covering map, it takes this picture, this graph, so and maps it and covers naturally this graph. So these two are, if this goes around -1, this goes around 0, this goes -1, 0, 1. So these 2 loops are mapped to this loop homeomorphically, and this loop is mapped twice onto this loop. So that's the covering map. And then the collapsing map phi, it maps this homomorphically here, this loop homomorphically here, and this is a loop around 1, so it disappears. So this thing is mapped to 1 point. And now if you take some lengths, so for example, you say that this circle has length 1. Okay, I don't have time. So you can put some lengths on this graph so that this is a covering and this is contracting. The contraction coefficient will be square root of 2. So you see that this is a contracting virtual endomorphism just by introducing lengths on this graph. So instead of talking about holomorphic dynamics, you can take this graph, and the theorem tells you that the limit will be the same as in the case of holomorphic dynamics. So it will be the Julia set. But here it's easy to iterate it. You can understand what are these spaces Xn. These spaces Xn will be again graphs. And if you draw them, you will get successive approximations of the Julia set. So I don't know. So you can construct models of the Julia set without you get approximation of the Julia set by graphs. The Julia set will be inverse limit of these graphs. You can do this also, find this unique limit, define it symbolically using symbolic dynamics. So that's what I want to do now, and then I will formulate the theorems about the dimension. So so suppose we have a self-similar group. So we have a homomorphism from G to the symmetric group times GD, and we can iterate this, and we get an action on the tree. So we have alphabet X, and we have associated action on the tree. So G acts on the tree. So consider now space of left infinite sequences, X minus omega. as a topological space. And let's identify two sequences if there exists a bounded sequence of elements of the group, meaning a sequence taking values in a finite set of the group, such that Gn of xn up to x1 is equal to yn up to y1. So we identify two sequences if there's endings, suffixes on bounded distance with respect to the group action. So the quotient of x minus omega by this equivalence relation is called the limit space. And the shift induces a continuous map. So that's called, we call this limit dynamical system. So the space in this theorem, this unique space, unique limit, is this limit space for the iterated monodromy group. So you can reconstruct, and this is a synthetic method to define this limit space. This works. So so the groups that are iterated monodromy groups of contracting virtual endomorphisms are not all self-similar groups. It's a special class of self-similar groups called contracting self-similar groups. So we say that this is contracting if it contracts the length of group elements asymptotically. So if when you apply G apply this Ritz recursion to an element of G, maybe after some iterations, then the length of each of Gi is less than some lambda length of G plus a constant, where lambda is in 0, 1, and constant is greater than 0. Maybe after some iteration, maybe it doesn't happen on the first level, but if you do several levels, this happens. So this is exactly the class of groups that appear exactly here. So we have a bijection. You have contracting virtual endomorphisms and contracting groups, and you can go from one to the other by these two constructions, the iterated monodromy group and the limit space. Okay, I'm running short on time, so I will formulate now the theorems about the dimension. So we are interested in dimension. We'll start with, for example, topological or covering the dimension of the limit space. How is it reflected in the group? So first fact is that, so the main theorem which I want to formulate about topological dimension is following. The topological dimension, covering dimension, or any type of dimension, inductive dimension, these are nice metrizable compact spaces of the limit space of a contracting group, so similar group, is equal to the smallest dimension of a contracting virtual endomorphism of simplicial complexes, of a simplicial complex. Of a contracting similar group G, together with that homomorphism, let's call it capital phi, with G phi as the iterated monodromy group. Okay, let's say faithful, because we pass the faithful quotient. So iterated monodromy group is the faithful quotient of the group. So in this model, you can have many different spaces. For example, I give you an example of Z²-1, where one virtual endomorphism was punctured disk, and the other one was a graph. So one had dimension 2, the other had dimension 1. Because there is dimension 1 model, it means that the limit space has topological dimension at most 1. So the Julia set of Z²-1 has topological dimension at least 1, at most 1, but it cannot have 0 because it's connected. So we conclude that it has dimension 1. As a corollary of this, we say that dimension of the limit space is equal to 1 if and only if this self-similar group has contracting so virtually free overgroup. In other words, there is some virtually free group F and a homomorphism into this recursion, so that this is contracting on the free group. So this virtual endomorphism contracts the length of elements of the free group, of virtually free group. And then when you take the faithful quotient, you get your iterated monodromy group. So essentially, dimension 1 happens only when it comes from virtually free groups or free groups. So for the Z²-1, in fact, you can see that the recursion on the free group is already contracting. As another corollary of this corollary is that there are very few finely presented examples. Namely, the only finely presented examples are virtually cyclic ones. And virtually cyclic ones are only cyclic and dihedral. So these are the only two finely presented self-similar groups with one-dimensional limit space. Okay. Another fact is, okay, I think we'll skip the other. I wanted to introduce the conformal dimension because that will be important. It has nice applications, and then the rest about conformal dimension probably you will hear from the talk of Nicolas Matebon. There is, yeah, I want to say also that we don't know, we haven't studied all classical or well understood self-similar groups correspond to dimension 1. We didn't really study any two-dimensional examples. So that's something that maybe it means that all our intuition about self-similar groups is wrong because we are used to one-dimensional examples. Okay, so here is the synthetic definition of the limit space as quotient of space of sequences. You should think of this as a kind of real numeration system, like real decimals or real binary numeration system on the limit space. Now, this space of sequences has canonical basis of topology, which are the sequences with a given finite word as an ending. Because the limit space is a quotient, these will be mapped to some compact subsets of the limit space, which I'll call tiles. So the limit space is tiled by actually they're not tiled, they might overlap, more like shingles. But still it's when the length of word grows, they become smaller and smaller. They are compact, so you cannot use them to define topology, but you can use them to define neighborhoods. If you take a point psi in the limit space, then a natural neighborhood will be to take all tiles of nth level containing it and then take all tiles which intersect those tiles. So take, let's say, Tn of psi is the union of tiles of the nth level intersecting tiles that contain, or also nth level, that contain psi. For example, on the circle, which is the limit space of that example that of angle doubling iterated monodromy group, the tiles are just the binary intervals. They subdivide into semicircles and in quarters and so on. If you do it n times, you get nth level tiles. If you take a point, you take the tile containing it and then tiles intersecting it. So that will be some neighborhood of the point. And we want to look at metrics with respect to which these neighborhoods are approximately round. Approximately round. Okay, that's the last thing I want to define, and then and that will be a kind of canonical class of metrics on the limit space. So we take metrics to define the following conditions. First condition is that there exists a constant C such that if you take that set Tn of psi, it is contained in some ball of radius R1 around psi with respect to that metric, and contains a ball of radius R2 of psi. So for all psi and all n, there exists R1, R2, such that this set is squeezed between two balls, and the ratio R1 divided by R2 is less than C. So we want these sets to be approximately round. And second condition, there exists alpha such and a measure mu such that measure of the ball of radius R is between C radius to power alpha and C inverse radius to power alpha for all radii less than diameter of the limit space of the space. So this is alpha's regularity, and then alpha is the Hausdorff dimension, and then conformal dimension of the limit space is the infimum of these alphas over all possible metrics. So that's a natural dimension for the limit space. And for example, if you take iterated monodromy group of a rational function, then the usual metric on the Julia set coming from the spherical metric from a spherical metric will be in this class. So if you take the Julia set of rational function, its Hausdorff dimension is an upper bound on the conformal dimension of the group. And finally, I wanted to advertise our joint result with Kenny, Zheng, and Nicholas Mattebon. We proved that if the conformal dimension is less than 2, then the group is Liouville. In particular, it is amenable. So in particular, if you have a rational function whose Julia set is not the whole sphere, then by a theorem of Macmillan, the dimension, Hausdorff dimension is strictly less than 2, so the group is amenable. So all iterated monodromy groups of rational functions are actually Liouville, and not only for finitely supported measures, for all measures with finite moment P, where P is any number greater than, well, for example, this dimension. So for example, for every second moment metric measure, you get Liouville. So that's, I think, the first time when this holomorphic dynamics was used to prove a non-trivial result in algebra, and actually really non-trivial. It was open for a long time whether these groups are amenable or not. That's okay. Sorry for going over time.